Hi everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty and today we'll discuss about the displacement work or pdV work. So in this lecture, first I will tell you the displacement work or pdV work with suitable example, and then we'll derive expressions for work output for different standard processes like constant pressure process, constant volume process, hyperbolic process, adiabatic process and polytropic process, etc. All of us know that the most commonly occurring work transfer processes are the processes where the expansion takes place under the influence of the pressure and the system boundary actually expands. To discuss the displacement work or pdV work, let us take a very simple example. You do have a piston and cylinder arrangement with some amount of gas contained in it. So you do have gas present here. This one is your cylinder and this one is your piston. Initially, the pressure is P1 and the volume is V1. This pressure P1 is more than the atmospheric pressure, and as it is more than the atmospheric pressure, definitely it will force the piston to move in outward direction, and the final pressure and volume attained are represented by P2, V2. All the intermediate states as well as the initial and final states are in state of equilibrium, and the process is a quasi-static process. Now, to discuss this, let us consider a PV diagram. You know that the initial condition is being represented by 1 and the final condition is being represented by 2. Let the path followed is this. Now, let us consider an intermediate point where the pressure is P. And under the influence of pressure, suppose it has undergone a very small change in volume and the distance traversed is dl. Let the area of the piston be A. Now, the area of the piston is A, the distance traversed is dl. The pressure is P and volume is V, corresponding to this intermediate condition. Now, what is the pressure force? Pressure force F is equal to pressure applied multiplied by the area of cross section. All of us know that the amount of work obtained when a force of F is applied and it causes a displacement of, suppose, say, distance x is F multiplied by x. Similarly, when we are considering this one, the pressure force F is PA and the displacement is dl. Now, the infinitesimal amount of work done, dW, is equal to F multiplied by dl. F is pressure exerted multiplied by area of cross section of the piston multiplied by dl. This ADL is nothing but the small change in volume. So this is pdV. Now, the total amount of work done can be obtained by integrating this. So this is integration of pdV from V1 to V. But all of us know that work transfer is a path function. So it has taken this path. It may take infinite number of paths to reach from 1 to 2. So the amount of work output will be different for different conditions. Now what we'll do, we'll consider some of the common processes and we'll derive the expression for work output following the first principle. We'll use the expression W is equal to integration of pdV from V1 to V2 to find out the work transfer for some commonly used processes. First, let us consider a constant pressure process, that is also known as your isobaric process. So for an isobaric process, work transfer is equal to integration of pdV from V1 to V2. It is a constant pressure process. Being a constant, P is taken out of the integration. So this is equal to P into V2 minus V1. So this is an expression when the process is a constant pressure process. Then we'll come to a constant volume process. So when it comes to a constant volume process, your V is equal to constant. So V is equal to constant, obviously dV will be 0. Now the work output will be 0. So for a constant volume process, the quasi-static work output is 0. Then we'll consider the hyperbolic process. So what is the hyperbolic process? Hyperbolic process is a process in which the product of pressure and volume remains constant. The hyperbolic process becomes an isothermal process when you are using ideal gases. And all the isothermal processes, particularly when it comes to ideal gases, are hyperbolic processes. So you can consider the isothermal processes to be a subset of the hyperbolic processes. Now, product of PV is equal to constant, that is equal to V1 is equal to P2 V2. Now, we will find out the work output for a hyperbolic process. Now, PV is equal to constant. This implies P is equal to C by V. So that we can substitute. So this is C by V dV from V1 to V2. C being a constant is taken out of the integration sign. This becomes dV by V from V1 to V2. So that is equal to C ln V from V1 to V2. You can represent this as PV because C is itself P multiplied by V into ln V2 by V1. You can also represent this as P1 V1 ln V2 by V1 or P2 V2 ln V2 by V1. All three expressions represent the work output for a hyperbolic process. Next one we'll consider is a polytropic process. All the processes may be represented in terms of polytropic processes by varying the polytropic index n. So what is a polytropic process? How it is being represented? The polytropic process is being represented by PV to the power n is equal to constant. And this implies P is equal to C by V to the power n. Now, what is the work output? That is integration of pdV from V1 to V2. You substitute this by C by V to the power n dV from V1 to V2. This becomes C multiplied by integration of dV by V to the power n from 1 to 2. So this is C multiplied by V to the power minus n plus 1 divided by minus n plus 1 from V1 to V2. So this is equal to C multiplied by V2 to the power minus n plus 1 minus V1 to the power minus n plus 1 divided by 1 minus n. So all of us know that PV to the power n is equal to constant. That is equal to P1 V1 to the power n and is equal to P2 V2 to the power n. So now this becomes P2 V2 to the power n multiplied by V to the power minus n plus 1 minus P1 V1 to the power n multiplied by V1 to the power minus n plus 1. Divided by 1 minus n. So here what we have done, to simplify this, we have substituted C by P2 V to the power n in this case and P1 V1 to the power n in this case while multiplying it with V1 to the power minus n plus 1. So ultimately you get the expression P2 V2 minus P1 V1 divided by 1 minus n. So this is the expression for work output for a polytropic process. Your reversible adiabatic process is represented by pV to the power gamma is equal to constant. Reversible adiabatic process doesn't involve any sort of heat interaction with the surrounding. Neither heat comes from the surrounding to the system or from the system to the surroundings. So in that case, the work output can be obtained by simply substituting N by gamma. While introducing the polytropic process, I have told you that any thermodynamic process may be represented as a polytropic process by varying the polytropic index. So now, let us consider a PV diagram . One to 2. This is the case where N is equal to 0. N is equal to 0 here. So when N is equal to 0, the expression PV to the power N is equal to constant reduces to P is equal to constant. That is an isobaric process. Similarly, you can have N is equal to 1, you can have N is equal to 2. When N is equal to 1, it becomes a hyperbolic process. That is, PV is equal to constant. Similarly, this is N is equal to infinity. Any process can be represented as a polytropic process. Now I sincerely believe that today's lecture on displacement work or pdV work will be extremely useful in understanding the concept of the pdV work or the displacement work, as well as the work output for different processes like constant pressure process, constant volume process, hyperbolic process, adiabatic process, etc. If you have any doubt related to this, please do put questions so that I can answer. Thank you very much for being with me for so long. I hope that we'll meet soon for another lecture in my YouTube channel, Erudispace.